Hi Year 12s, this is Mr. Lim again. We are doing the last video on empirical formula, hopefully. So let's just get into it. Okay, so we're going to be learning how to get empirical formula from multiple samples. Okay, so multiple sample sources is the important thing. All right, so in a lab it is common to do tests on different samples because it becomes too difficult to collect all the other stuff from from one individual sample. Okay, so because there are multiple things you need to collect, trying to collect them all from one thing is quite difficult. Okay, so let's have a look. So sample 1 might be combusted to collect data on carbon dioxide. Sample 2 might be combusted to collect data for water, and so on and so forth. Since these three samples might weigh different amounts, they can't be used to compare the number of moles within each element to each other. Okay, so that's what we're really doing in empirical formula. We're seeing how many moles there are in how many moles of each element there are in each sample. And so when we compare them, we can find the ratio. But if you don't have the same sample, you can't really compare them because sample 1 might weigh double of sample 2, and so therefore you're going to have double the amount of moles of that one element that you're doing from sample 1, which would be the carbon, and only half the amount of moles of the hydrogen, and therefore that ratio will be off if you compare sample 1 and sample 2 without thinking about their total masses. Okay, so to get the data we can compare against each other, we must convert the amount of carbon, hydrogen, and other elements into a percentage of the sample that they are from. So let's say we have two different samples which we are collecting hydrogen and oxygen from. Carbon and water from. So this one here we'll call sample 1. This one here we'll call sample 2. And in sample 1, we're going to collect the carbon from the carbon dioxide and get that information. All right. So to determine the percentage of each element, you have to get the mass of the element from the combustion data or whatever data is provided, then work out the percentage of the element within that sample. Okay. So what that's saying is that, okay, you do all your calculations and then you get the amount of CO or the amount of carbon within that sample. All right. Now that carbon will be different to the amount of carbon within sample number 2. It'll be slightly more considering the sample is slightly bigger. All right. So then the percentages can be used to work out the remainder of elements and thus be used to work out the empirical formula of the substance by converting it to mass. Okay, so what we're saying is that the amount of carbon is going to be different. The mass of carbon will be different. But the percentage of carbon will be the same for both of them. All right. So let's say that this one here, its carbon is maybe 32%. Which means that in this one here and that one there, both the carbons will be 32% of the total. Okay, then you do your water one on your sample 2, you get that, and you find out that the hydrogen is, like 20%, whatever. All right, and that will be the same for both of them there. Okay, the hydrogen is 20% of the sample. All right, then if you need to work out the oxygen, you just work out the percentage that's remainder. The oxygen is the remainder percentage. All right, so the concept is that the mass is different, but the percentage is the same. So we need to convert it into the percentage of that particular sample, and then we can apply that percentage to all different samples. All right. So here's a question which has multiple things, and let's see if we can work through this. Now you notice that it's only worth 6 marks, but when you see how much work I do, you'll have an appreciation of how fast you need to work through this thing. Okay, so we're going to work out what have we got? We got 1.51 grams of ester was combusted in excess oxygen and found makes 3.57 grams of carbon dioxide. Second sample, 2.1 grams, makes 2.04 grams of water. So let's get started. So first of all, we have to work out the number of moles of carbon dioxide. Now you notice that I'm not going to make this all neat because I've got to really squeeze this in to things. So this is from sample number 1. So the number of moles of carbon dioxide from sample number 1 is equal to 3.57 over 44.01. Okay, which happens to be some value 0.081 mole. And I'm just going to call that A. Okay. I can then get the number of moles of carbon, which will be equal to A. I can get then the mass of carbon, which will be equal to 0.974. I guess I'll show you how I got that. A times 12.01, which will equal to 0.974 grams. Okay, and we'll call that B. Then what I need to do is I need to work out how much of this first sample, that 1.51 grams, is carbon. So I need to work out the percentage of carbon from sample 1, okay, as your B over 1.51, which is that mass over here from sample 1. Okay, that times 100, which will get me 64.52%, and I'm going to call that C, right? So you notice that I'm saving all these numbers because I have to do an entire new calculation for water, right? So the number of moles of water will equal to what? 2.04 over 18.016, which happens to be 0.113 mole. We'll call that D, right? Then I can work out the number of moles of H, which will be equal to D times 2, which will be equal to 0.226 mole, which we'll call E, right? And then we can work out the mass of hydrogen, which will be equal to E times 1.008, which happens to be 0.228 grams, which we'll call F. Okay, and then I need to work out the percentage of hydrogen. Okay, which will be equal to F over 2.11. Where did that 2.11 come from? It comes from second sample weighing 2, so that's sample number 2. Okay, times that by 100, and I get 10.82%, which I'm going to save that as G. Now, you may notice that I'm saving values greater than the 6 that you're able to save on your scientific calculator, because I did this on my old graphics calculator. But you should recognize that your calculators only can save 6 values. So, actually, you can actually save 9 values, but you really don't want to use the X, Y's, and the M's and whatever. All right, so think about which ones you actually need to save. You need to save that one, and you need to save that one. So if you really wanted to, you could have just saved all of those as A and B. I like to save all my things just to make sure that I can go back if I have to. But, you know, without your calculators having that many saving values, you may just have to cut down on the things that you save. All right, so now I have the amount of carbon and the amount of hydrogen in that sample. I can work out the percentage of oxygen, which will be equal to 100, take away the percentage of carbon plus hydrogen, okay, which will be 100, take away, for me, it's C plus G, okay, those two values there, right? C plus G from 100 gets me 24.66%. Okay, which I'll save as H. Okay. So now that I've got the percentages of all three, now I need to convert them all into this. Now, it's really important to show that you're actually doing this, otherwise you don't gain the mark. Okay, the mass in 100 grams, I can't just write C either, even though that it's that value saved, because that's a percentage, not a value. So now that I'm just going to save, that's saved as C. Okay, the mass of hydrogen in 100 grams is equal to 10.82 grams, that's saved as G. And the mass of oxygen in 100 grams is equal to 24.66 grams, that's saved as H. All right, you have to show this working out, or at least this statement, because if you don't, you're going to be saying that, oh, I'm taking percentages and turning them into moles suddenly without really showing your chemical understanding. Okay, so you have to show that, otherwise you're not going to get marks in the exam. So do it. All right, so once you've done that, you can go get the number of moles of each substance. So C, H, and O. the number of moles will be equal to C over 12.01, which happens to be, what's that? 5.37, which will save us I. Okay, the number of moles. This one is G over 1.008, which happens to be 10.73, which I'm saving as J. Okay, and O is going to be H over 16, which happens to be 1.54, which I'm going to save as K. Okay, so now that I have those, I can work out which one's the smallest, divide by the smallest, which happens to be K, so that's going to be 1. This one happens to be 7, and this one happens to be 3.5, 3.49. Okay, if you saved your values in your calculator correctly. Okay, so I've got a half here, so this is not a simplest whole number ratio yet, so what do I got to do? I got to multiply it by 2, so therefore it's that becomes 7, that becomes 14, that becomes 2. So therefore it's C7H14O2. All right. And that's the empirical formula of this particular ester and venue B. So for 6 marks, all right, that's a lot of work. Okay, so you've got to really get fast at these. You've got to really learn how to save numbers in your calculator so that you don't have to keep on typing stuff out. I'd suggest writing things to like 2 or 3 decimal places just to show that you've worked it out, but you don't need to really show all of your things, so you can actually have, like, you know, those D times 2 and E times whatever, just to show that you are doing those calculations in that way. All right, here's another question for you to try. Okay, the final answer for this one, and you know, if you really want the working solutions, they're on Sector. And if you're watching this on YouTube, you can just go send me a message. I've never had someone send me a message on YouTube before, so maybe you can do that if you really want the working for this one. But it's C3H7NO is the final answer. You have a go at that and then see how you go in terms of that. And then if you have any questions, just ask me in class or, you know, on the internet. Up to you. Bye.